Resonance in series RLC circuit. Here, this is called resistor RLC are connected in series. VR is called voltage across the resistor, VL is called voltage across the inductor, and VC voltage across the capacitor. They all resistors, inductors, capacitors are connected in series. So across the AC voltage source, Vt is equal to Vm sin omega t. So here variable is called frequency. So in series resonance RLC circuit, by varying the frequency, we can understand the concept. Okay. So the resonance is nothing but the inductive reactance is equal to the capacitive reactance. XL is equal to XC. This condition is called resonance. XL is equal to XC is called series resonance condition. So at resonance condition, the power factor will become unity. Because of this, circuit will become resistive circuit. These two are equal and opposite. XL is equal to XC. That means XL minus XC will become 0. The voltage drop across the inductor and capacitor will become 0. Then the circuit behaves like a resistor. That's why at resonance condition, the power factor is become unity. Okay, XL is equal to XC, then XLX minus XC is equal to 0. So the impedance offered by the circuit is called only resistance. Z is equal to root of R square plus XL minus XC whole square. So XL minus XC term 0. That's why Z is equal to root of R square, that is equal to R. The circuit will behaves like resistor. So then power factor is unity. That is power factor is nothing but cos theta, that is equal to R by Z. Z is equal to R. That's why R by R 1. That is called unity power factor. So the circuit when XL is equal to XC and Z is equal to R is said to be in resonance. Under resonance condition, the resistance offered by circuit is called R. So minimum resistance, that is called R. So when resistance is minimum, that current will be maximum. Okay. So that's why it is called as a series RLC circuit under resonance. It's called as a current acceptor circuit. Okay. So Z is equal to R, the minimum resonance, minimum impedance or minimum resistance offered by the circuit at resonance condition. That's why it allows maximum value of current from the source. So under resonance condition, the current is maximum in series RLC circuit. So below resonance condition, above resonance condition, the current is different. Okay. So below resonance condition, its circuit will be act as a capacitive circuit. XC is more dominating below resonance condition. XL is more dominating above resonance condition. So below resonance, it acts as a leading power factor. Above resonance condition, it acts as a lagging power factor circuit. That means below resonance, it acts as a capacitive dominating. That's why it acts as a leading power factor. It offers leading power factor. Above resonance, inductor more dominating. So that's why it offers more lagging power factor. Okay, in series circuit, since current I remains same throughout, we can write like this. XL is equal to XC by multiplying I into XL is equal to I into XC. So I into XL is nothing but VL. I into XC is called VC. That is VL is equal to VC. Okay. So under phasor diagram, from the phasor diagram, we can understand under what is the phasor diagram under resonance condition. So under resonance condition, VL and VC are same magnitude but opposite sign. VL and VC. VL and VC are VL in this direction and VC in this direction. Same amount of magnitude and opposite. That's why VL minus VC is equal to 0. So at resonance, VL, VC will be cancel out each other. And then the supply voltage is equal to V is equal to under VR square plus VL minus VC whole square. Then VL minus VC is equal to 0. Then V is equal to VR. That is supply voltage will drop across the resistor R only. There is no voltage drop across the inductor and voltage drop across the capacitor. There is no voltage drop across inductor and capacitor. Only voltage present across the resistor only. Supply voltage drop across a resistor. Okay, under resonance condition. So resonance frequency, we know at a resonance frequency XL is equal to XC. Inductive reactance is equal to capacitive reactance. Inductive reactance is nothing but 2 pi FL, that is equal to XL is equal to omega L, that is equal to 2 pi FL. Xc is equal to 1 by omega c, that is equal to 1 by 2 pi r FRC. FR is called resonance frequency. 2 pi FR into L is equal to 1 by 2 pi FR into LC. Okay. Two pi FRL is equal to 1 by 2 pi FRC. Then simplifying, if FR square is equal to 1 by 2 pi square into LC, then FR is equal to 1 by 2 pi into root LC. So this is the resonance frequency. FR is equal to 1 by 2 pi into root LC. This is the resonance frequency. By substituting the values of L and C, then we will find the resonance frequency. The resonance frequency independent of resistance from this formula. So it is depending upon value of inductance and capacitance. So Q factor, this is called Q factor. So Q factor is nothing but voltage magnification during resonance. How much of voltage magnification under resonance is called Q factor. So it indicates how many times the potential difference across the L and C is greater than the applied voltage during the resonance. Okay. So the Q factor is nothing but VL by Vs. VL is equal to, we know, I into XL. Vs is equal to I into R under resonance condition. Only offer resistance. Voltage offered. Why? Only resistance. No? That's why we into I into R, then I cancel XL by R. XL is equal to omega L. Q factor is equal to Q is equal to omega R into L by R. Omega is equal to 2 pi F, 2 pi L by R. But FR is equal to 1 by 2 pi into root L C resonance frequency. By substituting here, the Q factor is equal to 1 by R into root L by C. Okay. And then just graphical representation resonance under resonance condition. So graphical representation, XL is equal to omega L. XL is equal to omega L means that is equal to 2 pi FL. XL is proportional to F. So inductive reactance is proportional to F means so when graph, it can be represented like linear. So inductive reactance is proportional to frequency. Frequency is increasing, inductive reactance also increasing. So proportionality, then we will get to the graph is called linear straight line from origin. So resistance independent of frequency. So resonance under resonance condition, it is independent of frequency. That's it. It's represented by straight line. Okay. So FR is equal to 1 by 2 pi into R into LC. That's why there is no relation between resonance frequency and resistance in under resonance condition. So that's why it's independent of frequency. Inductive reactance is proportional to the F. That's why inductance if the frequency increases, inductive reactance also increases. So from the origin, it is increases like slow ramp. Okay. Then as to capacitive reactance, capacitive reactance is called Xc. That is equal to 1 by omega C. Omega C is equal to 2 pi Fc. X is equal to 1 by 2 pi C. So then Xc is equal to 1 by F. So inductive capacitive reactance is inversely proportional to frequency. Then frequency increases, capacitive reactance decreases. Okay. So if frequency is 0, the capacitive reactance X is infinity. That means at 0, the curve starts from infinity, and then if frequency is infinity and X is equal to 0, okay. So that's why this is called exponentially is decreasing waveform. Okay, this is called capacitive reactance. Then impedance minimum impedance is minimum. So because of XL is equal to XC, that's why it's cancel each other. Then Z is equal to R only. So under resonance condition, the impedance offered by the circuit is only resistance. The resistance is minimum. Okay, it depends on only resistance. Impedance depends upon only resistance. Because of XL and XC cancel, then impedance is minimum at resonance condition. Only R, only resistance. There is no reactance effect. So then current I is equal to at resonance condition, I is equal to V by Z, Z is equal to R. Resistance minimum means current is maximum. So maximum current, the maximum current offer the circuit under resonance condition. Series RLC circuit offers, it draws more amount of current from the supply under resonance condition. Okay, so this is called resonance. And then coming to the power factor is unity at resonance frequency. The power factor is equal to cos pi is equal to R by Z. Z is equal to R, then R by R is equal to 1. That under resonance condition, Z is equal to R. Then power factor is unity. So this is the curves under resonance condition. So we are getting this expected this type of curves. Okay. So this XL curve with respect to XL versus frequency. This x-axis is called frequency and y-axis is called, for example, XL. Then XL versus frequency is called straight line from origin is increases like this. Okay, this is called XL, inductive reactance versus frequency. The next XC, so this is called XC. So at zero frequency, so maximum value of reactance. At zero frequency, XC is inversely proportional to F. XC is proportional to 1 by F. F is equal to 0, X is infinity, like this. So maximum value, and then if F is infinity, Xc is equal to 0. That's why it is near to the x-axis. So like this waveforms. So this curve is called Xc versus frequency, and this curve is called XL versus frequency, and then Z, that is called impedance. At resonance condition, it offers only resistance. The resistance line is called, this is the line parallel to the x-axis. Okay, so this is called minimum resistance. Under resonance condition, resistance will be minimum. FR is called under resonance frequency. At resonance frequency, impedance offers less. That is called only resistance. Below resonance, it's called this much of impedance. And here at resonance condition, at below resonance condition, so the capacitor is dominating. It is called Xc. Okay, at F is equal to less, the Xc is maximum. That's why at below resonance condition, capacitor is more dominating. That's why at less than frequency, 0 less than F less than Fr. So the frequency, power factor is called leading power factor because of capacitor dominating. This is dominating compared to this XL. Compared to XL, X is dominating. Capacitor is dominating. That's why leading power. And then above resonance frequency, Fr is less than F less than F in this region. So this capacitance is Xc is very less. X is less, but XL is more. Inductive reactance is more dominating compared to capacitor. It is dominating. Here, this is XL is more compared to Xc. Okay, Xc is very less, but XL is more, very high. So that's why inductor is dominating. That's why we will get at above resonance frequency lagging power factor. At resonance, unity power factor because of only resistance, copper resistance. And then next current, the curve is called, the black line is called current. At resonance condition, resistance minimum, that's why current maximum. Okay. At resonance condition, resistance minimum is current maximum. Under resonance condition, it draws more amount of current from the supply. It draws more amount from the currents from the supply, more amount of current from the supply under resonance condition. So below resonance less and above resonance is less because of impedance is more. Okay, impedance is added. Reactance is added to the resistance. That's why impedance is decreasing. Impedance less. Here impedance less. Here impedance more. Okay, impedance more. That's why current is less. And then next power factor. Power factor versus frequency curve. At resonance condition, power factor is high, unity. At resonance, Fr, resistance is called R. This is resistance is called R. Cos theta is equal to R by Z. Cos pi is equal to R by Z. R by R. That's why unity power factor at resonance condition. And at resonance condition, unity power factor. So like this, we can understand the series RLC resonance circuit. This can be understood by using one tool that is called P-Spice. So by simulating the circuit, okay, by simulating this circuit in P-Spice series RLC circuit, we can understand what are the waveforms. XL versus F, current waveform, voltage waveform, XC versus F, XL versus F. Okay, so this type of waveforms can be observed by using P-Spice. And then here open P-Spice schematic, P-Spice schematic, open like this. So in this P-Spice schematic, take one V sign, place here, and then next take one resistor R, and then next L, and then next C, capacitor C, press Ctrl R, series RLC circuit like this. So these are the different types of elements in series RLC circuit. Connect by using this wire like this. Connect these elements by using wire in this way. Connect like this. Connect in proper way. So this is called RLC and this is called V sign. So in this V sign, change settings like this. DC is equal to 0. AC is equal to 0. V of is equal to 0. And V amplitude is equal to take 12. Or V frequency is equal to take 1 kHz. 1 kHz frequency. Then save alter. Okay. Okay. So this is called V-sign parameters. Then coming to the resistor, take resistance R is equal to, for example, R is equal to, value of R is equal to, for example, take 100. Resistance is 100 ohms. Okay. And inductance is called 10 millihenry. Change like this, 10 millihenry. 10 millihenry. Inductance is equal to 10 millihenry or 1 millihenry. Okay. For simplicity, I'm taking here. Inductance is called 1 millihenry. And capacitance is called 1 microfarad. Take 1 microfarad. Change UF. Right here, UF. Millihenry means mH. Millihenry. Resistance directly 100 ohms. Take one ground, connect here. Take one ground. So like this. Circuit can be designed like this. 100 ohms, 1 millihenry, 1 microfarad. Okay. And current connect one current marker. Okay. Current marker. This is called current marker across capacitor. So under resonance condition, what is the current? We can find by using simulating. By simulating, we can find the what is the current under resonance condition. Okay, so that's why this is called sine waveform, sinusoidal input. That's why. So go to analysis, setup, and here enable AC sweep, and go to here linear, and here starting frequency 10 Hz and ending frequency, your resonance frequency from this RLC values, resonance frequency, by substituting the values of L and C, you will get resonance frequency 5 kHz. So that's why take end frequency 20 kHz, 20K. Okay, understood. So why here and entered 20K means resonance frequency 5K. So the waveform is generated up to 20K. This is called current waveform. Then save a series resonance, RLC resonance in series RLC, and then simulate. Then simulate. After simulate, you will get like this. So in this circuit, V sign, this V sign, AC 0, DC 0, AC 12, V of 0, V amplitude is 12, frequency 1 kHz. V amplitude is equal to 12, AC is equal to 12, frequency 1 kHz. And resistance is 100 ohms. Inductance 1 millihenry. Capacitance 1 microfarad. So after that, go to analysis, setup, AC sweep, and linear, starting frequency 10 Hz, ending frequency 20 kHz. Then close and simulate. So then you will get like this. The current waveform. Current versus frequency. This is called, go to properties, change like this. With So this is called current waveform. Okay. Current waveform. If you want to know, so what is the value of current under resonance condition and what is the resonance frequency? So enable this toggle cursor, best toggle cursor, and then this is called cursor peak. Press this cursor peak and mark label, and then display like this. Understood? So here, this is called x-axis, 5.007K. That is called our resonance frequency. This is called 5.007K. It's called resonance frequency. Under resonance frequency condition, so what is the value of current? Maximum value of current means, so 11.428. This is the current under resonance condition. Understood? So at resonance condition, a resistance minimum, for minimum, that's why current is maximum. Okay. So under resonance condition, resistance minimum, that's why current maximum. So it draws 11.428 amps current from source under resonance condition. So these are the characteristics index to current versus frequency under resonance condition, current characteristics. Okay. And then next, if you want to know the characteristics XL versus F. XL versus F. So go to, and also if you want to know the characteristic, what is the characteristics of voltage? So here remove this current marker and delete current marker, and then press voltage. Take voltage marker and simulate like this. This is called voltage versus frequency characteristics. Voltage versus frequency characteristics. Next. So voltage versus frequency characteristics means, so under resonance condition, VL minus VC is equal to 0. So VL, that is equal to VR. Okay. So VL is equal to, that is means VR is equal to, VS is equal to VR. The circuit offers only this current only. VL minus is equal to VR, V is equal to VR. So voltage across the resistor is equal to supply voltage. Okay. That is, supply voltage will drop across the resistor R only. Okay. So that means you'll get like this. Properties, go to properties, change the color like this. Width. Okay. Enable toggle cursor and peak, cursor peak, press cursor peak and mark label, and then it will be visible. So at resonance frequency, what is the resonance frequency? 5.0075K. That is called the resonance frequency. At resonance frequency, 363.227 voltage. Okay, that is called voltage across the resistor. Across the resistor is the maximum value of voltage drop across the resistor is called 363.227 on the resonance condition. The next, XL versus F. What is the characteristics XL versus F? So this, delete this by selecting the VC1 of 2, delete, and go to trace, add a trace, right here expression. So XL versus frequency. So frequency already is there in x-axis. That's why. So y-axis. So that is called, we have to write the expression, trace expression. So trace expression is called XL is equal to omega L, that is equal to 2 pi F into L. Okay. 2 pi F into L. 2 into, so go to here, macros. Pi is available here. 2 pi, and then go to n-log operators. 2 pi F and frequency 2 pi F into L. L is how much here in the circuit diagram? L is equal to 1 millihenry. 2 pi F into L. XL is equal to 2 pi F into L. That's why 2 pi f into L. L is equal to how much? 1 millihenry. That means nothing but 0.00001. 0.00001. Okay. So that is called XL. XL versus frequency versus curve. So here XL versus frequency curve changes like this. So again simulate and then you can easily understand. Remove this marker and press simulate and then open new window if the empty and go to trace, add trace, write this expression 2 into 2 pi f 2 pi f 2 pi into f frequency 2 pi f into L. L is called how much? 0.1 millihenry. That's why 0.0001 2 pi f into L. So like this. Straight line passing through the origin. Straight line passing through the origin. Like this. 5 edges, 10 edges, 15 edges. Like this. 2 kilo edges, 4 kilo edges, 6 kilo edges. This is called XL. XL versus frequency. XL is equal to omega L. Omega is equal to 2 pi f. 2 pi f into L. L is fixed. X is 2 fixed. Pi is fixed. And f is variable. And L is fixed in the circuit diagram. XL versus. So L 1 millihenry and 2 pi into f. Only variable frequency f. So we will get like this characteristics. XL versus f. Okay. So this is the XL versus f characteristics. Like this we will expect like this. XL versus f characteristics. XL is equal to 2 pi f. Units are reactance, ohms, but it is a frequency term is there. That's why it's in this output voltage waveform, it is also displayed in the form of edges only because of 2 pi f into L. L is called Henry, is fixed. Only variable is called frequency. That's why it is displayed edges. Okay. So in this way, we can get the inductive reactance versus frequency characteristic. Similarly, XC versus F. XC versus F. So then again simulate empty window will be generated. Empty window like this open and go to trace, add trace. Here what is the x-axis, y-axis called x-axis frequency, but y-axis is called xc is equal to 1 by 2 pi fc. XL is equal to omega L for inductive reactance. Xc is equal to 1 by 2 pi fc. So write this expression. So 2 pi fc 1 by 1 divided by, write like this expression with brackets. Trace expression 1 by 2 into and open bracket here also. Write like this. Two into pi into f into frequency f into c. Here c is called 1 microfarad. 1 microfarad. That's why 0.000 next 0001. That is called 10 to the power minus 6 and close two brackets. So 1 by 2 pi fc. Okay. So like this characteristics are photo properties change like this with so this is the characteristics of xc versus f. This is called frequency and this is called current reactance xc. Okay. At zero frequency, what is the value of reactance is called 160K, approximately infinity. Ideally infinity, practically maximum value of 160 kilo ohms. Okay, maximum value of kilo ohms. So 120, 40, like this, the two capacitive reactance on y-axis. Okay, then frequency on x-axis. So this is the curve frequency, curves XC versus frequency. Okay, like this, you can simulate by using p-squares. Okay, understood? So from this XL versus frequency straight line and XC versus frequency decreasing, like this also it can validate this. And also then next current is increases like this, voltage also increases like this. At resonance frequency, maximum voltage across resistor. So this is about series RLC circuit under resonance condition by using p-spice verification by using p-spice.